that they will think that I am not doing my job. No, it will be fast, so we do it fast. I think there's still some guys went for a break, so let's do.
Is this
I don't know. Something.
camera off so I can look? Yeah.
I need coffee. Coffee or nap? You have tiramisu? I would like, but I can't. I'm too much Higgs boson on. Higgs boson. Hello, Lydia. How are you doing?
Quite good.
Quite good? Some good news?
Not really.
No.
Every day is a good day.
First day is good day?
Every day.
Every day? Yes, but first day is my favorite day.
Why?
Because tomorrow is Friday.
Oh.
Like, we normally call first day a small Friday.
Oh. Friday.
Normally, first day with my friends, we always went out already first day evening for some small drink or something. So, from my young, first day was like a good day. You meet friends and you already relaxed. And Friday, you just work until lunch.
Then, what's your favorite place in Taiwan?
Favorite place?
Yeah.
I don't know. I was not thinking about it.
What?
City? Kaohsiung.
Why?
I don't know. It's very modern. It looks modern. No, I like Taipei, but I think the weather there is. What? Kaohsiung is what? Art. Oh, yeah, but exactly I'm saying that. I like more Taipei, but the rain is. It's too rainy. And too crowded. Too many people. Too many Taiwanese there. I don't know.
It's like Thailand.
What? Thailand?
Chill.
Chill?
Yeah.
Why?
No, just slower than the other cities.
Yeah. Thailand is. Yeah, some cities are smaller. Yeah. What's your favorite city?
Thailand, slower.
Thailand? I don't know. So Taichung is like. Yeah, that's true. And Penghu, I would say. Penghu is good. Penghu is good, isn't it? Okay, let's still take a small break. Do you think I can go? Or I think there's some guys left, right? So we do exactly the same what we did, the same geometry, everything. Only we just solve it now, okay? And I just want to tell you to the previous case, this facelift, so the argument or what we were assuming before, and we are also assuming here, that what happened is that we are assuming that I have a superconducting film, again I am just plotting like that, and I am driving a current. Okay? I'm driving the current in the superconductor. It's going into plane. And solutions which we done previously in the argument was that current is homogeneous. It does not depend on the X. It was everywhere the same. And we find this critical current. If you go over this critical current, then what happens also experimentally is that this current starts to be homogeneous. Normally it happens, it starts to have X dependence, that in some places it's stronger, in another is weaker, and this what normally happens. Okay, and if you have some defects, then around this defect, the current start to be even dissipative, okay? So this homogeneous picture breaks down, okay? Over this critical current which I found, okay? And also the solution about the superconductivity is not homogeneous, but getting X dependent, and then it's called like the phase slip. This is the name for that, okay? So now I am doing the same thing as before, but I'm not using the Gibbs free energy, but I'm just using directly the Ginzburg-Landau equations. So I'm just calling the title is the same, critical current of a thin superconducting film, but we are doing the calculation from Ginzburg-Landau equations. Exactly the same geometry as before. From minus D to D, current is here, and it carries some superconducting current Js, homogeneous. And I just need some boundary conditions, because I would need some boundary conditions, but this is exactly the thing. Imagine infinite slab, it's going everywhere, and you are driving a current over that. You don't need superconductivity for that, but you apply just Ampere law, and you know that if I am driving the current, then around the material there appears magnetic field, right? Biot-Savart Laplace law, and I know that there will be magnetic field. I need to use the right hand. So if my current is flowing here, then the magnetic field is going like that around the current, right? As you can imagine, if I have a wire and my wire is carrying the current, then magnetic field around the wire is going like this, right? So in this case, I don't have a wire, I have infinite cylinder or infinite slab, so the magnetic field is homogeneous, and then in the infinity it's going here and then returns back. Okay? Good. And this means that on top of the superconductor, I would have some magnetic field which is induced by the current. We can calculate it. If you tell me E, I will tell you what is BI. We just solved the Biot-Savart Laplace law. Okay? Fine? Good. And you see that on the top surface, we are having negative magnetic field. It's going against the z-axis. And on the minus D surface, it's going in this, okay? I have such chosen coordinate system. In all these books, they always choose that slab is along x direction, so that's why I just turn it, okay? So you can, if you want, you can turn it like that, and you will have a better picture. But this does not matter. So we see, and symmetrically, if the current is homogeneous, everywhere homogeneous, that value here and value here are the same, they are only having a different sign. This is important. Okay, doc? Good. So we know what is the magnetic field outside. And again, guys, solution. Okay, some clever people solve it, I don't know, 50, 70, 80 years ago, and we are just learning how they did it. Okay? So maybe you would say, oh, I would never alone come to that. Yeah, you would, maybe if you will think 2 weeks and spend less time on Instagram or something like that. You know, that time people didn't have Instagram, mobile phones. So they were more interested in physics. Now we are interested in everything else apart the physics. Okay, so you will be able to solve it, okay? So again, people start with the second Ginzburg-Landau equation. Assumptions the same. Current is homogeneous. I am also assuming that the order parameter is homogeneous. So it's not x dependent, okay? So I am writing the second Ginzburg-Landau equation. And again, I'm assuming f is homogeneous, not x dependent, and it's a real valued function. So all these gradients are gone, and I'm just getting this equation. Okay, this is the curl of magnetic field is equal to the current. So this is basically the current here. Again, straightforward solution. Immediate. Okay? Actually, the same problem we already had in this sheet number 2. That's the same thing. Okay, now we are just solving it differently. Okay, now I may compute magnetic field as before. Very similar. I just need to compute the curl of that, and I'm getting magnetic field, and I'm having magnetic field. It's very like this. But my magnetic field is now antisymmetric. Okay, this is the induced magnetic field. This is, I am not applying any external magnetic field. The magnetic field which appears is only due to the current which is flowing. Current is flowing to the plane. This is my slab. Right, my current is flowing. It's going to the blackboard, right, and it's creating this the magnetic field outside. So this is the current which is going outside. And we know the value here, and we know the value here. And this is the value here. So now we see that we need to satisfy this equation that on one surface it's a minus this, and on another it's that this. Why? Because this was this. Which tells me now that this coefficient should be equal to 0. Right? Because I need to something which changes sign. This is not changing sign if I'm changing x to minus x, but this is changing the sign when I'm changing x to minus x, right? So only this solution can survive. Am I right? How much am I right? 100? Okay, so 100 right. Okay? So basically this is the 0, okay, and I'm able to directly compute the magnetic field, okay? The same as we did before. So now I know that only this survives, the magnetic field is like that. Now I am applying the boundary condition, and I am able to specify this coefficient A1. Okay? So A1 is related to this BE, and this is the expression which I get. Similarly as we did before. Is that fine? Understand everybody? Perfect. And again, I'm doing the same thing here, that I am linearizing because I'm again assuming that the D over lambda is much, much smaller than 1. That's the assumption of the thin film. My X is not larger than D, and my F is not larger than 1. So this is also very small, even smaller than that. So I'm expanding everything. Cosine hyperbolic expand, sine hyperbolic expand. So I have it. Okie dokie. So now I see that the vector potential is roughly constant inside of that. Before, you remember, we get x dependent. Now we are not getting x dependent. But we are solving different problems, so that's no other problem. Okay? Great. And this is everything consistent, because if I know this, I can compute the current. This is this equation, which this is the London equation, but I don't have any gradient term because my wave function is real value. And I'm just plugging it here, and I'm really seeing that this is nothing else as the Biot-Savart-Ampere law. If I know the current density, which is constant, then VE constant is related with the current density like that. Yeah, this is this thing. If I will tell you the current density here, J, and this is very, very long, then I know what is the magnetic field and what is the magnetic field, this BE. And BE and the current density, which is not depending on X, are related exactly by this formula. We see it even, but you can really try your electrodynamics, and you just really solve this is the thing which is done, okay? So I'm just saying the thing is consistent. Fine? Good, so we know the magnetic field, we see the current, and we see really current is not X-dependent. There is no X-dependent here, so it's really homogeneous it should be. Now I'm coming to the first Ginzburg-Landau equation. Again, not kinetic term, I'm assuming F is constant, no gradient term because F is constant. First Ginzburg-Landau equation looks like this. One trivial solution that exists if F is equal to 0, but I'm not interested in the trivial solution. I just look for non-trivial. So it means one F I can cancel. So I'm getting this equation. I am substituting AY here. We just calculated it before. So I'm substituting here, and I see that AY is depending on 1 over F squared. This is to the second power, so I'm getting something to the power of 4 down here. And then I have minus 1 and F squared. I don't like this F to the power of 4 downstairs, so I'm multiplying all equation by F4, and I'm getting this expression. Okay, doc? So now you see, this is the equation for F. This is the equation for F, assuming that I know BE. Okay? Great. I'm just rewriting it. I'm introducing this critical magnetic field, bulk critical magnetic field, and then this equation is simplifying, and I'm getting this equation. So for any value of b, you just need to solve this equation. And you will know what we need to know. But you see, this equation is highly nonlinear. So it can have also more solutions, and not all of them will be physical solutions, okay? So we need to be a little bit careful, and that's why we need this picture. So I'm just introducing this function capital phi of f, just to show you that I am just plotting it graphically. So this is this function f to the power of 4 minus f to the power of 6 in the interval from 0 to 1, because my f is only from 0 to 1, and this is the values which I have. And you see that the graph of this function looks like this. Okay? So you see there are more solutions. So only half of them is physical. And we need to know how to find the physical solutions. And the story is like that. If there is not any magnetic field, if B epsilon is equal to 0, no current. Okay? No current means no BI. Then I have a superconductivity in the system. So my F is equal to 1. So I need to start here. If BE is 0, then the correct solution is this one. And now if I am putting BE non-zero, I start from here and I'm going, and this is the maximum value of the... It cannot happen that I am increasing the BI. If I'm increasing, I am stopping. I cannot go anywhere. So all what is here is not physical. This is this point with the current, which I made just before. Now I see it in the wave function. That I'm changing parameter BE, and I'm going, and then BE I cannot go even larger because there is no solution. Okay? David, what happened? I'm just trying to solve this equation, and I'm just claiming that if this BE is large enough, the right-hand side has the value which is larger than the left-hand side, or oppositely. So there is no the solution. Okay? And I'm just also telling you that this equation has more solution, and we just should need to be picky because only those are correct solutions. Okay, this graph. And how we know it? Once again, we need to use the physics, because if Fe is equal to 0, or Fbe is equal to 0, then I need to solve this equation. But if Be is equal to 0, it means there is not a current, but there is just the perfect superconductor which is unperturbed, and it means F is equal to 1. So this tells me I need to start at the site F equal to 1. Great, so now let's again find the maximum values until which we can solve this equation. So the equation we can solve up to that point, and after that, there does not exist solution. And we again say that we need to find this critical value. So again, we make a derivative equal to 0. Okay, so I need to make the derivative. Okay, so I need to differentiate this function. Okay, 4 minus 6, blah, okay, super, 2/3 is the solution, okay? And this is exactly what I had before. Critical field was 2/3 of the psi 0 squared. So this is again this 2/3 which I had before. Okay? Do you see it? Do you see now 2/3? I just take this function phi. I just make its derivative. And I request this derivative to be 0. And I'm saying this happens at that point. Okay. So this is the critical value of, sorry, this I need to rewrite to capital T of that. So with this critical value, this is the thing which I'm having. Since I have the critical F, I also know the BE critical, which I can have. So this is the maximum value of BI which I can have that the solution still exists, and this is the value of BE. But just what we saw before, BE is related to the current. Right? Here. So maximum value of the BE is related to the maximum value of the current which you're having. So I'm making the story from the opposite side. Historically, it was done from that side. Then come the Bardeen and he put it on the opposite side. Okay? He write the functional and come from the velocity. That guy comes from the wave function. Okay? Only this is the difference. But the story is basically exactly the same. So we know the relation between critical F, this is the critical order parameter. We know the critical value of the BE, okay, it's written here. And we know the relation between BE and current. So we are getting this critical density, which is here. And this current is related to IE, IE to BE, BE to E, so this is what we had also before. Okay? So this is the critical current of the film, and you again see the story, okay, that it's go like this. And if you plug the critical value of everything, you just get the formula which I had before. So the critical current density is equal to some constant which does not depend on anything. This is just the fundamental constant. And then you are having the property of the superconductor, which is the coherence line and the magnetic penetration line. Yeah? So you see that the critical current is independent of the thickness of the film. Below that, you have beautifully homogeneous superconductor. Slightly above that, things start to be more complicated. Our solution is not any more valid. We need to look for different wave function ansatz. Okay? But the system is still above this current, still superconducting. This can be shown, and I'm just telling you, I will put it as a homework that check that the free energy still is negative. So it's a superconducting case. So this is coming to the same results from the opposite side. Okay? So just the main summary of today, and this is the end of the lecture of the Ginsburg-Landau and about the applications. So we studied first what is this critical, this is a self field, this is the magnetic field which would be generated by the current. So the supercurrent is flowing and it's creating the magnetic field. And this magnetic field is depending on the thickness. Okay, so this critical magnetic field, this BE, is depending on the thickness and is linearly proportional to the thickness. Okay. The second thing which we derived, but we derived it as a first, was the in-plane critical magnetic field, which goes 1 over D. Okay, and this thing, if the D is very, very small, then you clearly see that this guy is always much, much smaller than this guy. The critical field in plane is always larger than the critical current induced field. And this means that if you have a supercurrent flowing, it is creating magnetic field, but this magnetic field is never so strong that it will kill superconductivity itself. This equation tells me that if current can induce the magnetic field which will be larger than that, then the magnetic field of the supercurrent is killing the supercurrent. Okay? But we are having in the opposite limit, so this is not happening. Make sense what I'm saying? Okay? Once more.
Okay.
No, seriously. Like this means that we find that what is the critical magnetic field when the superconductivity is gone. And this is this value. Okay? If the current is flowing over the superconductor, it's also create magnetic field. This magnetic field, superconductor is thin. So this magnetic field is also penetrating inside of the superconductor. If this magnetic field which is generated by the current would be larger than this, you will kill the superconductivity by yourself. You are moving so fast that you kill yourself. I would say it like that, okay? Did you get it? That's why I'm always saying about the Russia, that they are so big that they cannot sustain how big they are. Big, to all big countries applies the same. Okay? So this is the thing. But that's what I want to tell you, that this is important thing. In the thin film, the destruction of the superconductivity by a current is not identical as the destruction by the magnetic field. But then I wanted to say that basically you don't need to worry that magnetic field generated by the current will be so much that it will kill itself. Okay, this is excluded. Okay. And this is about these things about the phase slips, which I was trying to tell you, that what happens if you go over this critical current or over this magnetic field, then only what happens is that the order parameter is not homogeneous, it changes. We need to look for the different solution, okay? But it's still superconducting. That's all for that. People are able to measure it. Everything perfectly matched with the Ginsburg-Landau theory in the conventional nice superconductors. Okay? So I would say this is the beauty of this theory. There are two differential equations, and there are ways how to solve it. We do some assumptions. It's always like start like this. Let's assume solution looks like that. And there is some physical intuition behind. And then you just solve the rest. Okay? And then you say, okay, it matches what I see, so my guess was good. If I don't see that it matches, then I say, I don't need to blame the theory. I need to blame my ansatz. That what I put as a starting point was maybe not good. Okay? For example, other solutions, but I will maybe come to that later, are the vortices. And the Abrikosov showed that there is a very special solution of the Ginsburg-Landau equations which are vortices. And the people then measure them and see they are quantized. And it also comes from the Ginsburg-Landau theory. So also the story about the vortices and how they behave is hidden there. But I think you will be bored if I will always talk about this Ginsburg-Landau and these partial differential equations. So I am postponing. We are finishing that for the moment. And from next week, we go to the microscopic theory. Try to explain what is this force that forces electrons to create the Cooper pairs and why they are stable, why they are bound, and try to understand this from the quantum mechanical principle. Okay? So that's the story for the next time, and we will see how far we will go. And then we will finish the Ginsburg-Landau BCS theory, and then we will discuss the Bogoliubov-de Gennes and Josephson effect. And maybe we will return then again to vortices, depending on the time. Okay? I don't hurry up. I rather think that you understand the things. You know, superconductivity was developed in the 50s. There were, I don't know how many Nobel Prizes, maybe 6, 7 Nobel Prizes for the superconductivity. So if you have expectation that during one semester I will tell you everything, of course it's not possible. Okay, so the story is whole unit. I think we can study 3 years and then maybe we will cover everything, every details. Okay? Good. Do you have questions? Then let's call it a day and see you next week. I will upload my slides and also homework sheet. I will put some problems for you to solve. And that's it. Okay, David, thank you.
Okay.